Shri Sai Ram. Welcome to this study of coordination compounds, where in this segment we will deal with the bonding that are present in metal carbonyls. We have studied many theories now, and now our study is going to be revolving around one ligand, which is carbon monoxide, which we call it as carbonyl ligand. This is a neutral ligand and it does not have any sort of charges. And we have seen in crystal field theory that neutral ligands will act like dipoles in their interaction with the metal carbonyls. So here our study is going to be with respect to the homoleptic ligands which are present. So let us see some aspects of this metal carbonyl structures which are present. Most of the transition metals will form these type of homoleptic carbonyls. Now homoleptic indicates that there is only one type of ligand, and that ligand is carbonyl. And these are well defined structures. We have tetrahedral structure for tetracarbonyl nickel, pentacarbonyl iron. What you are able to see everywhere in all the examples that are given are, they have various structures like tetrahedral, trigonal, bipyramidal and octahedral. That depends on the number of ligands. Tetrahedral is formed when tetracarbonyl is there. Trigonal bipyramidal is formed when pentacarbonyl is there. Octahedral is formed when hexacarbonyl is there. So this is how the variation in number of ligands will let the structures form by itself. And you are seeing that charge in every single case is 0. Now why is that 0? Because it is not having any counter ion, and carbonyl is a neutral ligand. So therefore in these neutral ligands, the overall charge will be 0, therefore the central metal ion will also have a charge of 0. So what are certain important aspects of this? Now what does this metal carbon bond say is that it will have both S as well as P character in their cases, and what is important in these parts is that the S character and P character are given by the sigma and pi bonds which are being formed. Now for example, I am taking cobalt. Remember, this is capital C capital O, this is capital C small o. This indicates cobalt. Atomic number of cobalt, we know it to be 27, so that will be 4s2, 1, 2, 3, 4, 5, and then the 6th and 7th are present here. Now this is in interaction with carbon monoxide. So what happens here is, carbon monoxide being a ligand, it will donate a pair of electrons to the system. So this bonding which is there is a normal one, which is a sigma bonding, which you have studied in valence bond theory. But what is seen here is that in carbon monoxide, when you study the molecular orbital theory of this compound, we see that there are many orbitals which are empty. So here there is something called as back bonding. Now what is this back bonding? It means that the normal bonding between the ligand electrons to the central metal ion is happening. Along with this, the paired electrons of the metal is given back to the ligand form which are available. And why it is happening here is because we can have empty orbitals in the case of carbon monoxide. Now remember, this ligand is a combination of carbon and oxygen. So the empty orbitals which are there in carbon monoxide can accept the paired electrons from atom also. Now this is only possible in the case of this carbonyl ligand which is there, and this effect where the back bonding of electrons from metal to ligand, we call it as synergic effect. So this is the normal sigma bond, whereas this is the pi bond which is formed, the reverse bonding between cobalt and carbonyl. Now that necessarily need not be cobalt, it can be iron and various other d block elements also. So let us see some important aspects of that part which in these carbonyl groups. So the first point there says that the metal carbon bond possesses both S and P character. The MC sigma bond, the M indicates central metal ion, C indicates carbon of the carbonyl group. It will be formed by the donation of lone pair of electrons from carbonyl carbon. This is the normal thing that was happening, but what is special in this case is the MC pi bond, which is the donation of pair of electrons from a filled d orbital. This is the filled d orbital, whereas these are unpaired electrons. From this filled d orbital, the electrons are transferred back to the ligand which is present. So, this is an important aspect in this bonding in metal carbonyls, and since this is exclusively happening with carbon monoxide, we study the bonding separately. So, let us see some of the other aspects in this case. This is a pictorial representation. As you are seeing, the carbon monoxide is the ligand. The normal donation from the electrons of carbon monoxide, it is shown like sigma, the central one which you are able to see. What is the pi bonding is? It is the reverse bonding, back bonding. The other word is synergic effect or synergic bonding, where the electrons of the d metal atom will be given to the ligand, and that ligand will have the empty orbitals which can occupy. So, some of the structural aspects of this homoleptic carbonyls: tetrahedral, looks more or less similar like the CH4 methane structure that we had studied. Trigonal bipyramidal structure of iron carbonyl group which is there. We can also see the octahedral structure of the chromium complex, and then we have another two compounds where it is a dimanganese and dicobalt compound. So, what has happened here is that two manganese atoms, they are in contact with the ligands, along with that the manganese atoms are held together. Similarly, the cobalt one CO2 CO8 which is there, each cobalt is in combination with 4 carbonyl ligands, and a bond has been formed between the cobalt atoms also which are there. So, this is a representation of structures of these homoleptic metal carbonyls, and these are certain pictorial representations, 3-dimensional representations of the same compounds that we happen to study, the nickel compound, iron, chromium. Additionally, you also have an example of tungsten which is W. So, tungsten is combining with the 6 carbonyl groups which are there, and obviously that also will be octahedral because you have 6 ligands in that. And the other two which are there, that is the manganese compound and cobalt compound, they are large in nature. So, they are interconnected by the d metal atoms also, as well as the ligands which are being present there. So, this is a representation of this metal carbonyls which is there. Now, looking at the stability of the compounds which are being formed. Now, all these coordination compounds are not formed at a single stretch by themselves. So, it is formation where, suppose I have a compound ML6. Now, what does this ML6 indicate? M indicates the central metal ion, L6 indicates the 6 ligands which are present, and we have seen in all the earlier parts that whenever there are 6 ligands, you generally represent them like this. This is the on the plane, above the plane, below the plane. This is how you represent it. Now, this ML6 does not form directly by the interaction of the metal with 6 ligands. It does not form like this. The formation is step by step that it tends to form. So, how does it form? In the very first step, you basically have here where the metal which is present will react with the first ligand, and the reaction could be reversible in nature because this is a reaction that is happening between ligands which are various properties. So, the formation here is Ml, a combination of metal and ligand. And how does this combination takes place? The lone pair of electrons in ligand are donated to metal. Now, how do we give it? Because it is one of the steps in the system, I will name the rate constant as K1, and this we have studied from first year equilibrium chapter, where the rate constant is dependent on the concentration of product formed divided by concentration of reactants which are there. So, the product is Ml and the reactants are M and L. That is how the concentration is formed. Similarly, as you have seen the first step, now that comes to the second step, where the Ml that is formed in the first step, what is this Ml? It is a metal and ligand combo, is combined with the second one, and that is how you get it as Ml2. What does this indicate is the metal ligand complex that is formed in the first step reacts with another ligand. And what will be the K2 value of this? K2 will be equal to Ml2 divided by M, and another part is only the L which has been taking place here. So, this is how we can write the rate constants of various compounds which are there. So, this is the rate constant of first step, this is the rate constant of second step. Now, what if suppose there are 4 steps in this cases? So, as you see here, if it is a 4-step reaction, you will observe that the K1, K2, K3, K4 can be written similarly like the way which are written here, and this can be represented as stepwise stability constants of all these products. Now, what do we do with the stepwise stability constants? The overall constant of this reaction can be denoted by a form called as beta, and that beta will be equal to the overall stability constants that are shown. Now, whenever we show beta, we show it as beta n, but because I have 4 components here in the example that I have taken, I can show it as beta 4. Suppose if I have to restrict myself to the example that I have taken on board here, I can write it as beta 2 is equal to K1 into K2. So, a reaction which is there can be formed in any number of steps. If you have to form Ml6, it has to be formed in 6 steps. If you have to form Ml4, you have to form in 4 steps. This is the formation of Ml2, where only with 2 steps you can form and beta 2 you can write. So, what is this beta n is basically the total number of steps that are being present. Now, the reciprocal of this beta, which is nothing but 1 by beta, can be called as the instability constant of the system. While this is called as association constant of the system, the dissociation constant is nothing but the reciprocal of beta, which can also be called as instability constant of this compound. So, this is all about the metal carbonyls which are being present here and the stability of the coordination compounds which we can see. Thank you. Sai Ram.